In this video, we are given the following problem. We have the derivative 2x of a general function f of x, and this is equal to this function itself. And we are now asked to find this specific function f of x such that this equation holds true. Or in other words, we need to find a function which for each x is equal to its derivative. Now this is the simplest form of a differential equation. However, don't let words scare you off, because it's quite similar to what you know already. For instance, let's say that you're asked to find the derivative to x of x to the power of 3, simply the derivative of a specific function. And we're asked to calculate this derivative. And I'm sure you know that this will be 3 times x to the power of 2. And this is very straightforward, because we are given a very specific function, x to the power of 3, and we need to find its derivative. However, now we're not given this specific function, but rather a general function. And instead of having to calculate the derivative, we are also given the solution already, namely the function itself. And in this case, we need to find a specific function such that the derivative is equal to this function itself. So basically, it's calculating derivatives, but with a twist. Now, there are two ways of solving this differential equation, or finding this specific function. The first one is just to plug and try. Just think of functions that we know on the top of our head and calculate its derivative and see whether it's equal to this function itself. The first function that we can think of is the easiest function we can imagine, namely the constant function, where f of x is just a constant number. Okay, let's see what derivative it gives us. So we have the derivative to x of simply a constant number, and this gives us, of course, as we know, 0. Now, since 0 is not equal to our original function, this function is not the function that we're looking for, namely a function which is equal to its derivative. So let's go to our second guess then. The next easy function that we know is f of x being equal to simply x, the linear function. So let's see what this gives. This gives us d over dx of the simple function x. And we know, of course, that this will be equal to 1. And here again, we see that x is not equal to 1, and therefore this is also not the function that we're looking for, because the function that we're looking for has the following, that d over dx of our function is equal to our function itself again. And in fact, we can already see that our function will definitely not be any power of x, because we know that if we derive any power of x, so d over dx, of x to the power of n, then we simply get the following, n times x to the power of n minus 1. And we see that this will never be our original function. And therefore, any power of x, or any polynomial function by extension, will not comply with this constraint that we're actually looking for. So we need to look elsewhere. Let's, for instance, try a trigonometric function. f of x is equal to the cosine of x. Well, what do we know about the cosine of x? That its derivative, so d of dx of the cosine of x, is simply equal to minus the sine of x. And of course, minus the sine of x is not equal to the cosine of x, so we again conclude that this is not the function that we're looking for. Let's then try, for instance, our f of x is equal to e to the power of x, and you might have already guessed that this is actually the solution. So we have d over dx of e to the power of x is of course equal to simply e to the power of x. It's one of the basic derivatives. And we see here that we indeed have that the derivative of our function, in this case e to the power of x, is indeed e to the power of x. And we have indeed our condition to be fulfilled. So we know that the solution is actually e to the power of x. And we got this by just trying some functions. Of course, this is not a general approach on solving such an equation. So in order to be a bit more mathematically minded, let's go to our second method, which is actually a general method to solving such easy differential equation. And this method is called the integration method. And as you can imagine, it has something to do with integrating our original equation. And just to recap, it was d over dx, so the derivative to x, of a general and unknown function f of x is equal to this function itself. So the derivative of a function is equal to a function itself. Now, what we can do is rewrite this a little bit, namely we will split this derivative sign, d over dx, in a d in the numerator and the dx in the denominator. And what we will do is take the d and now consider it being a differential of f of x. And we will place the dx to the other side of the equality sign, where we have f of x, and now we have multiplied with dx. So this might not be the most mathematically sound method, but it works either way. Let's see how it exactly works. In the next step, we try to take all of the f of x's to one side of the equality sign. So basically we're moving this f of x to the other side and dividing it in that way. So we have d of f of x divided by f of x, and what remains on the other side is simply this dx. What we're then going to do is to integrate both sides of this equality sign. And if we actually do this, then we see that on the right hand side we just get the integral of dx, which we know to be x. And we're going to ignore the constant term that can be added with indeterminate integration. And on the left hand side we have d of f of x divided by f of x. And if we call f of x equal to u, or just rewrite it, then we get, of course, the integral of 1 over u, so that's this 1 over f of x, du. Now we know the integral of 1 over u du. This is simply the logarithm of u, the natural logarithm, the ln. So we can also write that right here. So we get the logarithm of f of x. And so what we see here is that we get an algebraic equation for our function f of x, where initially we had a differential equation, so an equation with a derivative in it. We can solve this algebraic equation very simply by just exponentiating both sides of the equality sign. We know that e to the power of the ln of x is simply x itself. In this case, this x will be f of x. So we get that f of x on the left hand side is equal to e to the power of x. And this is exactly the result that we got before by just plugging it in and seeing what we got. And we got this result now by a systematic way, going from a differential equation to an algebraic equation and then solving this algebraic equation. Now note that from this step to this step, we omitted this constant term which we often get by indeterminate integration. And you are indeed right that we should take it into account, but I will leave that for a next video. If you found this video useful, consider giving it a thumbs up. And you can of course also check out other physics and mathematics videos on the channel. And with that, I thank you for watching and I will see you in the next one. Bye.